here's what we need to know about this lesson 50, geometric mean. Now, before we get to geometric mean, we need to understand, at least have an idea. If we have a right triangle, notice JKL is a right triangle. If we draw an altitude on this right triangle going from the right angle K to the hypotenuse down here, whenever we draw an altitude going to the hypotenuse of a right triangle, it creates similar triangles. All three triangles, the original right triangle and these two smaller right triangles we've created, are all similar to each other. And how they relate to each other, how we can find some missing pieces of these, that's where we get to our geometric mean. But before we get there, notice all three, these two created are similar to each other, and these two are both similar to the larger triangle created at the beginning. Notice here, altitude drawn to a hypotenuse, we know we have three similar triangles there. All right, now our geometric mean. Geometric mean, remember when we talk about a proportion, we have the mean values, or the two values in the middle, and the extremes are the smallest and the largest value. Those are the extremes. The medians are the numbers in our proportion that are kind of in the middle. So if we were to find like the geometric mean of 2 and 12, well, we know if we were to average these, we would get 7. That is the arithmetic mean. But the geometric mean would be that we want to find the one number that satisfies both mean positions, and the two numbers we're taking the geometric mean of will have to be the extremes. So we would cross multiply. 2 times 12 is 24. X times x gives me x squared. I take the square root of both sides. So the square root of 24 is equal to x, which reduces to give me 2 root 6. Or I could even type that in my calculator and get a decimal. This would be about 4.90 to 2 decimal places there. If we want to find the geometric mean of 3 and 12, well, once again, averaging these would give us about 7.5, but the geometric mean is the one number that satisfies the mean positions. We cross multiply, we get 36 equals x squared, and that means x would be 6, a nice, pretty number. Find the geometric mean of 2 and 9. Well, 2 and 9, the average, or the arithmetic mean, would be 5.5, but if we wanted to find this mean, 2 and 9 need to go in our extreme positions. X is that one number, the geometric mean, that satisfies the mean positions. X squared equals 18. X equals 3 root 2, or simplified to the nearest 10th, which is what they asked. The nearest 10th would be 4.2. All right, now what is the application of this? It all has to do with those similar triangles we were talking about earlier. Both of these corollaries are coming out of that theorem that I talked about earlier. The altitude drawn to the hypotenuse creates similar triangles, creates 3 similar triangles. So notice here it says, if the altitude is drawn to the hypotenuse of a right triangle, we know that's creating similar triangles, then the length of the altitude is the geometric mean between the segments of the hypotenuse. So let's draw this out. Here's a right triangle. You can draw that right triangle however you want it to, however you want it oriented, but we have a right angle. If I draw the altitude to the hypotenuse, I know the altitude is my geometric mean of my two segments of my hypotenuse. That means that x, my altitude, is going to be that one value that satisfies both mean positions when the segments of the hypotenuse, which has now been split into two segments, are in the extreme positions. This second corollary here, again, begins the same way. If the altitude is drawn to the hypotenuse of a right triangle, then the length of a leg of that original right triangle. So let's think about this leg over here. Then the leg is going to be the geometric mean. It's going to be the geometric mean. It's going to be that x position, that one value in our mean positions, between the hypotenuse. So remember, we've drawn the altitude of this right triangle. The leg is the geometric mean between the hypotenuse, the whole hypotenuse, and the segment of the hypotenuse closer to that leg. X, one of the legs, is the geometric mean between the hypotenuse and the segment of the hypotenuse closer to that leg. All right, so if we want to find these missing pieces of our hypotenuse, we know the entire length of the hypotenuse is 5, but we want to find A and B. We want to find those two missing pieces. Well, B, I can see right there that B is a length of the hypotenuse, and I have the leg closer to that. I know that the length of a leg is the geometric mean between the hypotenuse and the segment of the hypotenuse closer to that leg. So I'm going to put 5 and B in the extreme positions. I cross multiply, 16 equals 5B. We divide by 5, and B would be 16/5, or that is 3.2. Okay, that was B. Still need to find A. Well, we know B is 3.2. We can subtract that from 5, and we see that A is going to be 1.8. It really is that simple, because that is our segment addition postulate. But I want to show that geometric mean still works to find A over here also. A is the segment of the hypotenuse that's closer to the leg 3. I know that the leg of my original right triangle is the geometric mean, so it's in the mean positions between the segment closest and the entire hypotenuse. This gives me 9 equals 5A, divide by 5, A equals 9/5, or 1.8, which is what we had said, adds up to 3.2 to get us that 5. So once again, it makes complete sense. When we see it all put together, like, okay, these two do add to give us 5, we should feel really, we should feel validated. That's what I'm looking for. Let's look at E right here. We want to find the value of X. We're given the altitude this time, and we know the altitude is the geometric mean of the two segments of the hypotenuse. So 3 is the geometric mean between X and 5. So 5X equals 9. X would have to be 9/5. We just did something like that. 9/5 we know is 1.8. Here, we just did a problem like this. We know that 12 would be the geometric mean between 13 and B. 5 would be the geometric mean between 13 and A. So that would be a really easy problem to do also. All right, finally some application. Look here, we have the situation. Jayden's building a truss for a shed. Jayden needs to find the lengths of the truss brace AY, XA, and ZA, but I'm not going to find them in that order. Look, if I wanted to find the altitude, YA, even though that's the first thing they list, I know the altitude is the geometric mean between N and M. That's not possible for me right now because I don't know N or M. I would be trying to find something knowing nothing that I need. So I'm going to first find M. I know the piece of that hypotenuse right there can be obtained through that second corollary, knowing that the length of a leg of my original right triangle is the geometric mean between that piece of my hypotenuse and the entire hypotenuse. So I work through this. And that comes out to be 0.64. That's 64 hundredths of a foot. Since they didn't say, my go-to is around the 2 decimal places there. Over here, I want to find n. Well, it is as simple as just subtracting from that 1.56. It really is. So I take 1.56, subtract away my answer. I know this is going to be left to be 0.91 feet. And again, you're welcome to do the geometric mean over here. We have the information for it, but it is not necessary because we know the segment addition postulate. Finally, to find P, my altitude is the geometric mean between the two pieces of my hypotenuse. So P does go in the mean positions, and I have 0.64 and 0.91 in the other two. And that comes out to be about 0.77 feet, about 77 hundredths of a foot rounded to 2 decimal places.